Let's look at some processes that take place in a rigid tank where we'll need an energy balance to solve for some unknown variables. Water, initially saturated vapor at 4 bar, fills a closed rigid tank. The water is heated until the temperature is 400 degrees C. For the water, determine the heat transfer in kilojoules per kilogram of water. Kinetic and potential energy effects can be ignored. Well, let's lay out our 5-part storyboard, starting with a schematic. So I've drawn a rigid tank, and the tank is filled with water, and I've drawn the boundary around the water molecules. So the water molecules form our system. And the volume of this tank is constant, and since it's a closed system, the mass of the water is constant, and therefore the specific volume of the water in the tank is also constant. So here's our given data. State 1 is at 4 bar and its quality is 1. In other words, it's a saturated vapor. And it's heated until it reaches a final temperature at state 2 of 400 degrees C. Now let's look at that on a TV diagram. Here we have our vapor dome. And state 1 is a saturated vapor, so it's right here on the right side of the vapor dome at a pressure of 4 bar. So our 4 bar pressure line goes up to the right, always being horizontal underneath the vapor dome. And so state 1 is at 4 bar, and it's a saturated vapor. Now, when this is heated, being having a constant specific volume, or this is a constant volume process for a closed system. So the process is going to follow this vertical line up to state 2, which is at 400 degrees C. We'll model this as a closed system, ignoring any changes in kinetic and potential energy, and it is a constant volume process. And we want to find Q over M, which we often write as a small q. It's the heat transfer of energy into the system in kilojoules per kilogram of water. So let's write an energy balance for this closed system. Since kinetic and potential energy effects have been eliminated, we can say that delta U is Q minus W. But no work can be done by a rigid tank. A rigid tank simply is not equipped to perform work. So we can eliminate that as well, and we're left with an energy balance of delta U is equal to Q. Now we can rewrite this. Delta U is just U2 minus U1, where these capital U's have the units of energy. And I can rewrite that as the mass of the system times the change in specific internal energy. And that is equal to Q. I can divide both sides by the mass, and I get Q over M. It's just the change in specific internal energy. So we can go to the water saturation table at 4 bar and get some properties for this initial state. We see that the saturation temperature at state 1 is 143.6 degrees C. And we know that U1 is U sub G, which is 2553.6 kilojoules per kilogram. And we know that V1 is V sub G because it's a saturated vapor. And that's 0.4625 cubic meters per kilogram. So now we have two properties that define the final state. The temperature is 400 degrees C, and we know that V2 is equal to V1. So we want to go to the superheat table, and we want to go to the superheat table at 400 degrees C. And we're looking for a specific volume at 400 degrees C. The specific volume being 0.4625 cubic meters per kilogram. Well, we can't find a line with that exactly. What we do find is that here on this subtable at 5 bar, and here's this subtable at 7 bar, we find that the specific value we're looking for, 0.4625, is between these two tables. And I've rewritten that here. So at the pressure of 5 bar, I have a specific volume of 0.6173, and a pressure of 7 bar, I have a specific volume of 0.4397. And we're looking for something in between. Well, we need to find the value of the specific internal energy, U. So it's somewhere in between these two values. And so what we're going to do is interpolate using our known value of V to find the value between these two values of U. So let's interpolate this value of internal energy. I like by just separately calculating a fractional value, which tells me how far I am between the two rows in the table. And in this case, it's going to be our known specific volume minus the specific volume at 5 bar divided by the specific volume at 7 bar minus the specific volume at 5 bar. And I plug those numbers in here and I get my F value of 0.8716. So now we can write our interpolation expression where we say U2 is the internal energy at 5 bar plus this fractional value F times the internal energy at 7 bar minus the internal energy at 5 bar. And I put those values in and we get U2 as 2961.2 kilojoules per kilogram. Well, all that's left now is just to plug those values into our energy balance, and we have Q divided by M, or small q, but the heat transfer per unit mass is just the change in specific internal energy. And we looked up U2, or we calculated U2, and we looked up U1, and finally, so we get Q over M, or small q, is 407.6 kilojoules per kilogram.